In this video, we're going to talk about molecular geometry. Molecular geometry is simply a way to predict the shapes of molecules, okay? Prior to using molecular geometry, you have to know how to create or rather draw the Lewis dot structure of a molecule, okay? So, uh, once you understand Lewis dot structures of a molecule, and if you haven't done that so far, I would recommend going back to the Lewis dot structure video and learning how to draw Lewis structures. A couple of things to note about molecular geometry. Molecular geometry is based off a central atom. Okay, so let's imagine you have a central atom out here, and there are electron groups around the central atom. Okay, so let's say you have 4 electron groups around this central atom. I'm just denoting them by straight lines. These electron groups, they're going to try to repel each other. Okay, and because they're all negatively charged, okay, so they're negatively charged, they're going to try to move as further away or far away from each other as possible, okay, and as a result of that, the molecule will take a certain shape. What's crucial to understand is, if you have a molecule with many different atoms, it's always the central atom which dictates the shape because everything arranges around a central point, okay? So, negatively charged electron groups, they will move furthest away from each other to minimize repulsions, and as a result of that, the shape of the molecule will come about. A couple more things about these repulsions. There is a priority in terms of repulsions. So, a lone electron pair will repel another lone electron pair very strongly. They take up a lot more space. Number 2, so that's priority 1. Priority 2 is a lone electron pair will repel a bonded electron pair or bonded electrons. And then number 3 is bonded electrons will repel other bonded electrons. So if you think about priority, number 1 is greater than number 2 and 2 is greater than 3. That's the priority. You could also write this as 1 greater than 2 greater than 3. All right. Let's just get right into it. So far we've been talking about the central atom. Now what we need to do is we need to understand electron geometries around the central atom. Okay, so to understand electron geometries around the central atom, we need to understand what constitutes an electron group around the central atom. Okay, so what's an electron group? So I'm just going to write that out here, electron group. So any lone pair, so lone electrons, that's an electron group. Another electron group would be a single bond. A double bond is also an electron group, and a triple bond is also an electron group. So the lone pair is typically denoted like this in a lobe. A single bond is denoted with a single line. A double bond is denoted with a double line, and a triple bond is denoted with a triple line. Pay close attention. Each of the lines is not an electron group. The whole thing is an electron group. So that's one electron group, that's another one, and that's another one. Okay? Okay, so in terms of electron groups, there are essentially 5 electron groups or 5 categories we're looking at. Okay? And these are electron groups around the central atom. Okay, so around the central atom. The first category we'll look at is linear. Okay, the second category we'll look at is trigonal planar. Let's go ahead and take a look at what linear looks like. It's pretty self-explanatory. Linear means, if you imagine this to be two bonds, the red to be two bonds, okay, and the green is an atom in the center. There'll be two more atoms on this side, but these two bonds, they're going to space themselves out as far from each other as possible, so that's going to be linear. The third group is the third electron geometry, or the third group is called tetrahedral. The fourth is trigonal bipyramidal, and the fifth is octahedral. So these are the 5 electron geometries, okay, around the central atom. Let's dive into this a little further to understand what this means. So when we talk about linear, so if you imagine there's one central atom out here, there's essentially any bonds coming out of the central atom are going to look like a straight line, okay? Trigonal planar is going to, if you imagine the central atom out here, it's going to look like a ceiling fan, three-pronged, three-directional. Tetrahedral is kind of going to look like so let's focus on linear electron geometry, okay? So take, for example, you have a molecule HF, okay? If you draw the Lewis structure of HF, you will get HF, H bond with a single bond to HF, and then there are lone electrons around HF. Now, since this is just a two-electron system, a two-atom system, you have to imagine that this is the center of the molecule, the middle of this bond, that's the center of the molecule, okay? And if you imagine the hydrogen being on one end and the F being on the other end, that's essentially a straight line, because you're looking at literally those two electrons between the two atoms. That's a straight line, okay? So therefore this would be linear in geometry as well. So we're going to write molecular geometry, that's going to be linear, okay? And if you imagine this little bond out here, if you imagine the hydrogens on one side and the fluorines on the other side, then that bond is a straight line, okay, linear. Another example of linear would be, let's take a look at carbon dioxide, where the Lewis structure looks like this. Now for carbon dioxide, you can take a look at this model out here. Notice carefully, the green is the carbon, and then you have the two oxygens. So those two red bonds, those are connected, those are the double bonds connected to two oxygens on the end. But as you can see, if you look around the central atom, it's basically a straight line. Therefore, that's linear as well, okay? So that would be linear. How many electron groups in the middle? One electron group, right? One. I'll just write it out here. That's going to be one electron group. And out here in this case, you're going to have two electron groups connected to the central atom. So that's two electron groups, okay? All right. Let's talk about trigonal planar electron geometry, okay? So take for example BH3. The Lewis structure of BH3 is this. And if you notice, there's one boron in the center, so the atom in the center, and you have 3 electron groups around the central atom, 3 electron groups. So the structure of that is going to be looking like this, right? Notice carefully, there's 3 atoms coming out all around, and then if you actually look at it just like this, you can see that all of those are in one single plane. So three-dimensionally, that is the shape. So therefore, trigonal planar, single plane. Take an example of another molecule, SO2. The Lewis structure of SO2 is actually, there's a lone pair out here, and then you have a double bonded oxygen on one side and a single bonded oxygen on the other side. Notice carefully, around the central atom, there are 3 electron groups. Okay, so the number of electron groups are still the same, 3 electron groups. However, the molecular geometry out here is going to be dictated by the actual bonds and not the lone electron pair. Okay, so even though the shape is 3 electron groups, the overall shape is trigonal planar, just like we looked at this. But the molecular geometry, we got to ignore the electron pairs. So if you kind of take a look at that and just pull off one of the bonds, which can denote the electron pair, then what we have is a bent shape. Therefore, the molecular shape is bent. Just remember, molecular shapes are dictated only by the atoms and the bonds, not by any non-bonding electrons, which in this case is the lone pairs. Let's direct our attention to tetrahedral electron geometry. Okay, so I'm just going to show you a model of a tetrahedron, and that's basically 4 electron groups around the central atom. So if you look at that central atom, the black carbon, in this case it's carbon, it could be any other atom. You have four bonds coming out of the carbon, and when you arrange them 3-dimensionally, they kind of look like a tripod. So see, they can sit like a tripod, okay, with one of the legs pointing upwards. And if you flip them over, it's the same thing. Okay, so 3-dimensionally, that's how they arrange themselves. The bond angles out here are, notice carefully, if you draw this in 2 dimensions, then the bond angles are going to be actually smaller, but we're looking at a 3-dimensional molecule, therefore the bond angles are much larger. Okay, so that bond angle is 109.5. Okay, all right, so let's take a look at the first example out here. The first example we'll look at is CH4. I'm just going to write that out here, and the C is connected to 4 hydrogens, and when you depict this in 2 dimensions, you draw a dotted line showing one of the hydrogens going back behind the board, and then a darker line, a darker wedge, showing this hydrogen, which denotes that this hydrogen is coming out towards you. And these two are in the plane of the board. Okay, so if I take this model out here, that'll kind of look like this, where see, that hydrogen is coming out towards you, that one's going away from the board, behind the board, and then these two are actually in the plane of the board. Okay. All right, so the molecular geometry out here is the same as the electron geometry, so tetrahedral. Now what's going to happen is, the next example we look at, we're going to replace one of these bonds with a lone pair. So if you look at NH3, I forgot to put electron groups around central atom, there's 4. If you look at NH3, it's going to be, nitrogen with a lone pair above it. And then you have hydrogen, then another hydrogen. So that's 3 hydrogens below it. That actually kind of, if you pull off one of these bonds, that's what NH3 would look like. Again, we don't count the lone pair, so that kind of looks like a pyramid. If you connect all the lines, these are the faces of the pyramid, but it's 3-pronged, right? Therefore, this would be, the molecular geometry would be trigonal pyramidal. Okay, and then the next example we'll look at is H2O. The Lewis structure for H2O is you have 1 hydrogen coming out, 1 hydrogen going away from you. You have a lone pair, so that's a lobe out there, and then another lone pair out there. Okay, again 4 electron groups, but now we omit the 2 lone pairs. So taking this same thing of nitrogen, I just pull off one of the bonds, one more bond. So there's the 2 lone pairs, the little black. And then notice carefully, if I flip this over, you see how that's bent now, the shape. So therefore, water is bent. Okay. Let's talk about trigonal bipyramidal electron geometry. So in this case, there are actually 5 groups around the central atom. Okay. So let's take our first example, let's say PCl5. If I draw the PCl5 with the 5 chlorines, it would be, I'm just going to draw them in 2 dimensions out here, and then we'll talk about the 3-dimensional shape. So the Lewis structure would look like this, plus the lone electrons on the chlorine, on each of the chlorines. All right, so now what kind of a shape does this have in 3 dimensions? All right, so if you look at this, this is a 3-dimensional structure with a central atom and then 5 groups equally spaced around it. So that's what it's going to look like in 3 dimensions. If you kind of envision this, if I just hold this a little differently, if I hold this like this from these 2 groups out here, notice carefully that forms a pyramid. And if I hold this way, that forms a pyramid as well. But an easier way to look at this is to just hold the bottom out here and see that's a trigonal, and then you could form a pyramid on top. You could flip it over, hold that bottom, and then you could form another pyramid on top, which is trigonal as well. So therefore the name trigonal bipyramidal. So this structure is, the shape, the molecular shape is trigonal bipyramidal. Now let's take a look at another example. So in this example we have SF4, so we're just going to have 4 fluorines. I'm just going to space them out as equally as I can, and then there's a lone pair on the sulfur, and then each of the fluorines also has 6 lone electrons or 3 lone pairs. Okay, so now what shape does this take? If we take that same structure PCl5 that we had and we just pull off one of these, then that would dictate the shape. So now before you pull off, we have to be a little strategic. And what I mean by strategic is, if you kind of look at this shape from here versus here, it doesn't look the same. It's a little different. Okay, so let me try to explain what's happening out here. There is an angle. If you look at this angle out here, that's a 90-degree angle, okay, between the top. So these are the axes, okay. So these axes, these are called axial bonds, okay. And these bonds, the 3 bonds in the plane, in this plane, the horizontal plane, are called equatorial bonds, okay. The axial bonds are actually at 90 degrees to any of the equatorial bonds. See, I'm going to spin this and see. They look like right angles. They're all at 90 degrees, and the same story is for the bottom, 90 degrees, okay? Now, the equatorial bonds are actually 120 degrees to each other. So if I just flip this over, notice how that's 120 degrees. So that's greater than 90, that's 120 degrees to each other. And here is where we have to make a decision. Well, when the bonds are 120 degrees to each other, they're actually further away from each other. When they're 90 degrees to each other, they're closer to each other. So if I had to remove one of these bonds and replace it with a lone electron pair, if you recall, lone pairs take up a lot of space, okay? So a lone pair bonded pair interaction is going to require more space than a bonded pair interaction. So if I insert a lone pair, it makes sense to insert a lone pair along any of the equatorials, because that's giving me more space because of the greater bond angle. So I'm just going to pull off one of the equatorials out here, and when I pull that off, I have this shape resulting. Now this shape, if you kind of flip it, and if I hold it this way, notice carefully how this becomes a seesaw. Okay, there you go. It's a seesaw shape, right? It's a seesaw shape, right? So therefore this shape is called seesaw. Let's take a look at another example of BRF3. In BRF3, once we draw the Lewis structure, we have the 3 fluorines connected to the Br, and then each of the fluorines has lone electrons to complete the octet, and then the bromine, the central bromine, actually has 2 lone electron pairs, okay? So again, it's a 5-electron group system, but now we have to figure out what shape does this take. So if I take the same 5-electron group system that I use for SF4 and I remove one of the electrons, now the question becomes, which one do I remove? Do I remove one of these or do I remove one of these, right? And turns out you can actually remove, if you will still remove one of the equatorials because of the greater bond angle, okay? And so we'll remove one more equatorial, and when we remove an equatorial, we're left with something that looks like the letter T, okay? And therefore the shape out here is T-shaped. The final scenario for a 5-electron group is XCF2. In XCF2, this is what it looks like, XC with 2 Fs. We have lone electrons on both the Fs, and then we have 2, 2, and 2. So there are actually 3 electron pairs on the central atom. So if we kind of take our same trigonal bipyramidal base and we have to remove, we will remove this one because that's going to create the maximum spacing between the remaining 2 bonds, and therefore we end up with a linear shape, okay? So the shape out here is going to be linear. The next thing we're going to take a look at is octahedral electron geometry. So let's take a look at an example of SF6. The Lewis structure for SF6 is there are 6 fluorines all around the central sulfur. There you have it, okay? And there are 6 electron groups, 1, 2, 3, 4, 5, 6, okay? So now what we want to do is we want to take a structure that kind of spaces them out symmetrically. So here you have the structure, you have the central atom, you have 6 electron groups, you can count them, 1, 2, 3, 4, 5, 6. Notice carefully, if I hold the structure like this, and if this is the plane of the board, 2 of them come out towards you and 2 of them go inside the plane of the board, okay? So that's important to understand. So if I had to draw this 3-dimensionally, this would kind of look like, see, that fluorine goes away, that comes out towards you, that goes away, that comes out towards you, and then there's the top and the bottom fluorines, okay? Now, as I mentioned in the case of trigonal bipyramidal geometry, these 2 bonds, the bonds going straight up and down, are the ones that are axial, and then the bonds that are going away and towards you are the equatorial bonds, okay? So now, what structure does this, what shape does this entail? This is called an octahedral shape, okay? Why? Because if you actually connect all the ends and make a face from each end, you get 8 faces, okay? So I'll kind of try to show you 1 face, 2 face, 3, and 4. And then at the bottom there's 4 more. So the shape of this is octahedral. Let's take a look at another example, BRF5. Notice carefully, you still have 6 electron groups, but one of them is a lone pair. So just like we discussed in trigonal bipyramidal geometry, if you had to remove a lone pair, you will probably remove them from the equatorial positions. Now it's more important in bipyramidal than in octahedral, and the reason for that is because in bipyramidal, the bond angle between the equatorial bonds was greater. In this particular case, the bond angle is actually the same, whether it's axial or equatorial. So here you have the axials and here you have the equatorials, okay? You can see the bond angle between the axial and the equatorial is 90. But if I flip this over like this, see the bond angle between the equatorials are 90 as well. Now, so in a sense, this is a more symmetrical shape than bipyramidal geometry, okay? Because no matter which way you spin it, it looks the same. So see, if I hold it this way, it looks the same. If I just spin it 90 degrees, it still looks the same. So it doesn't matter. Pull off any one. When you pull off any one, what you're left with is something that's a plane. Notice carefully, that planar has 4 points. If you connect the points, you end up with a square. Okay, so that's a square. But notice carefully, there's also an axial bond. So if you connect the squares, you get a pyramid. So it turns out this is square pyramidal. So that's the geometry, square pyramidal. The last scenario we'll look at is XCF4, where the geometry is going to look like this. You have four fluorines, the Lewis structure, you're going to have four fluorines. You have two lone pairs on the xenon in the middle. You have going to have the rest of the lone pairs on the fluorines. And if I take the same structure out here and pull off one more, what I'll do is I need to pull off this one, okay, the remaining axial bond. So if I pull off that remaining axial bond, now I actually just have a square. Notice carefully the square, and it's in one plane. So that's a square planar geometry.